Cool. Then I'm really happy that we're starting really strong with a large group of people here today, and Alex, who even prepared a problem set for us, which I think is really exciting. So I'm definitely looking forward to going through that, and also looking forward to the two classes. So take it away, Alex. Thank you.
Yeah, thank you, Rico. Yeah, so I guess for the benefit of the recording, the Go links being shown here, go/Brainiversity Info Theory will actually get you these slides if you want to follow along. Go Brainiversity Info Theory PS is the sort of problem set, just some fun problems I created to kind of get you thinking more deeply about these topics. I encourage people to kind of, collaborate, talk about it with other people. You don't have to do them, but I think they're fun. I encourage them. And then the last one, Brainiversity chat room created for Brainiversity. Please use it. Talk about, use it for this course, use it to talk about the problem sets, use it just generally. Okay, so hi, I'm Alex Alemi, researcher here. And I was asked to kind of give a basics of information theory sort of course. So we've got 2 sessions scheduled, this sort of 90-minute one and the next week. And kind of my rough plan is today, I really want to focus on trying to talk about some of the sort of basic functions in information theory for use in machine learning, like KL divergence, relative entropy, mutual information, and try to build some real intuitions about what. And then next week, the plan is to kind of dive into some applications. So talk about things like information bottleneck, or kind of representation learning, contrastive bounds, variational bounds on mutual information, these things that are kind of showing up in papers these days. And I would love to, after today, give me some feedback, depending on how things go, how the time goes, we can move things around. And especially for next week, let me know things you would like to hear about. And in so much as I feel I have any authority to talk about them, I'd be happy to. Okay, and also, please interrupt me. Let's kind of chat. Let's talk. Let's make this, not just me sitting in this empty room talking to a computer for 90 minutes. Okay. Information theory. What is information theory? Now, on the one hand, I sort of have to apologize in the sense that if you go to the library, you go or something, you pull off a book about information theory, most of what I'm going to talk about is not going to be in that book. Information theory broadly is about communication. That's sort of where the field is rooted, and that's where most of the advances and work is done. I feel remiss to not talk about that at all. So I do want to give you sort of a flavor, a taste about what the kind of central tenets of information theory classically are before we kind of talk about more machine learning things. So here we go. Here's the godfather of information theory, Claude Shannon, who in 1948 wrote A Mathematical Theory of Communication when he was at Bell Labs. A year later, it was published as The Mathematical Theory of Communication after it was realized how sort of general the framework was and how sort of expansive his discovery was. And he very much was concerned about communication, right? How do you send signals? How do Alice and Bob communicate over noisy channels? And we have him, information theory is really to kind of thank for all of the things we use today, all of these beautiful, cell phones and, 5G, CDs, DVDs, all of our sort of explosion in information richness, the things that we can kind of stream and download and view and store and save, all digital media, really is, literally rooted in these sorts of discoveries. So just as sort of like a timeline, kind of what are we talking about? So 1948, Shannon published The Mathematical Theory of Communication, which we'll talk about the central result just for a few minutes. But then since then, information theory has been rooted in discoveries for communication protocols, like codes, they're usually called, as well as like compression systems and algorithms. And here are just some sort of highlights, some of the big ones to come out, like things like Reed-Solomon codes developed in the 60s. Those are literally the codes that are used on DVDs, CDs, things like that. Polar codes, very recently, 2008, actually sort of the first set of codes that realized Shannon's vision of that we're about to talk about. And that's going to be the basis for things like 5G, which people are rolling out now. So I just wanted to kind of give some things there. So, okay, what is the central result? Why is this guy so famous? Why is information theory a thing? It's about communication and communication over noisy channels. So what does that mean? So here's a beautiful little visual example from McKay's book, Information Theory, Inference, and Learning Algorithms. Imagine you're trying to send that Dilbert cartoon to your friend, but you're sending it over some noisy pipeline. So every time you send it, every pixel has a 10% chance of getting flipped. So you try to send the Dilbert cartoon, and you get this dirty Dilbert cartoon on the other side. That's suboptimal. So how do you get around this? How do you communicate in light of this noise? Now, intuitively, the simplest thing to imagine, is to just repeat yourself, right? If you don't send the Dilbert's cartoon once, you send it 3 times. And then on the receiving side, Bob decides to kind of take majority rule across the 3 things that he observed. You'll see that, let me get my little, are people seeing the laser pointer? Yeah? Good. So if I send it 3 times instead, each one of those kind of gets noised up, but independently. And so if Bob takes majority rule across these 3 things, then it gets cleaner. It still has some noise, but it's cleaner than 10% noise. Now, before Shannon, several people have developed certain kind of codes, like this repetition code, or actually Hamming codes came out the year before. But these all have the property that in order to, if I really wanted to guarantee that I could communicate something perfectly, like in the limit that I want the probability of an error to go to 0, codes had vanishing rate. In the sense that if I really wanted to avoid any chance of error, like part in a billion, I might need to replicate the code 100 times, but that's 100 times slower that we're able to communicate. So they all had that property. The most remarkable thing, the reason why Shannon is famous, is because he asked the kind of abstract question, in the space of all possible codes that anyone could develop, like what are the fundamental limits on this diagram? And the noisy channel code, there exists codes such that if you wanted to communicate with in the limit that the probability of error goes to 0, you want perfect communication. You can actually achieve perfect communication at a finite rate. And that's kind of mind-bending. I mean, that's world-changing, literally and figuratively world-changing. And that's why Shannon is famous. That's why information theory is a thing. You can communicate with a vanity of error at finite rate. And that's why kind of the digital world exists and can exist. So I'm not going to talk about this, not right now, right? I hope to, by the end of next session, revisit this topic and hopefully with a lot more clarity. But I wanted to give you a taste of, really kind of the fundamental result of information theory. If you're interested,
before we leave, can I ask a stupid question on your
please.
previous slide? So what does rate mean? Can you explain the x and y axis of the plot? I didn't.
Yeah. So sorry. So here, what's happening is this is like the probability of error. Think of it like that. The probability that you could perfectly communicate. And these 2 are the same plot, just one's on a log y scale and the other one's not. And then rate, just think about it as like literally how fast you can communicate. So think of it as how many. Like in this case, I just want to invoke the notion that if I was trying to send a cartoon, if I replicate 3 times, I'm sending it at a rate of 1/3 of a Dilbert cartoon per, send.
Gotcha.
And what Shannon told us is that there are, for a fixed length message, basically in the limit that I don't need to pad the message, I don't have to pad the message infinitely in order to achieve sort of 0 probability of error. And that's the remarkable thing that I'm not going to tell you about. But if you do want to learn more, there's lots of fantastic books. I recommend Elements of Information Theory by Clevery Thomas and McKay's Information Theory, Inference, and Learning Algorithms. Also yesterday, I think it was, Frank Nielsen tweeted out like a kind of set of his favorite books.
Does the code depend on the message? Like, do you have to instantiate a new code for every message you want to communicate? With no error or something like that?
There are different codes that and they kind of work sort of fundamentally different ways. Like the difference between Reed-Solomon codes and Polar codes and stuff are kind of quite distinct. But I guess there are, in the way that there are algorithms that you don't have to, algorithms the result is different depending on how you change the data, but you can kind of code up a universal thing independent of the medium you're trying to send, right? And there should exist a code like that, like a protocol.
I think another way of asking that question is, if you fix the code, is the rate going to depend on the message, or it's always fixed?
Yeah, that's kind of what I was trying to. Yeah, thank you.
So yeah, in practice, is it going to depend on the message? In some sense, no, and that's maybe part of that's I think one way to describe how Shannon might have cracked the nut, in the sense that ultimately in sort of information theory, in the way that Shannon described it, there isn't really any like moral aspirations we assign to a message, in the sense that, you know, like one person's trash is another person's treasure. They're all just kind of collections of bits. And the kind of like the job or the principle or the thing that we're after is, can we tell the difference between different messages? So yeah, I want to say the codes work independent of the message that you're trying to send. But the way that they achieve their thing is they obviously modify what you do send, right? You have to modify your message send it in order to be able to send it without error.
Yeah, and I think, if I'm not mistaken, but intuitively, I think that for a fixed code, there should always exist messages that the rate approaches 0, right? It gets as close as we want to 0. I mean, adversarial, I think that if you fix the code, there should always be ways to build adversarial messages that the rate is as close to 0 as we want. Is that a correct intuition, or?
Oh, so yeah, so sorry, the actual rate at which you can send doesn't depend on the message. It depends on the properties of the channel on which you're sending. And yes, if you are allowed to adversarially choose the channel, like if you get to be some demon who reaches in and injects noise in very peculiar ways, then I do think that you could design a channel on which that rate at probability 0 for any particular message kind of goes to 0. But under the assumption, information theory works on the assumption that you have a channel that's sort of fixed. So the properties of the noise in the channel are sort of fixed independent of the message. And if you had a fixed channel, then independent of the message, you could communicate at finite rate with probability, with sort of vanishing probability of error.
I see. Thanks.
Yeah. Okay. So what are we going to talk about? So what we're going to talk about is the parts that came out of this whole enterprise that I think are tremendously useful for machine learning. And that part of it, the way I sort of view information theory, is as it's about measurements. It's about measurements. It's about measuring things having to do with probabilities. It's about measuring how much data influences your belief about hypotheses. It's about measuring how close two probability distributions are to one another. It's about measuring how similar two random variables are to one another. And coming out of Shannon's enterprise is a unique and special of measurements and relationships that we can use and abuse, and are already using and abusing, you know, whether you know it or not, in machine learning. And that's what I want to talk about. So the cast of characters today is we're going to talk about kind of 4 measurements, 4 functions: weight of evidence, relative entropy, and mutual information. And broadly, what is weight of evidence? It's going to be a measurement that, given data and 2 hypotheses, like given data, it allows you to try to distinguish between 2 hypotheses. It involves 3 things. Then relative entropy, we're going to ask, what if I only have 2 distributions? How do I sort of measure 2 distributions with respect to one another? With entropy, we're going to get even simpler. How do I just measure, you know, a single distribution? And with mutual information, we're going to ask, how do I sort of measure 2 random variables with respect to one another? Something about how close or how similar they are. And now we're just going to try to build some really sort of intuitions about what these things from, how they interact, and stuff like that. Here's just their sort of definitions. I don't want these to, you don't necessarily have to know what these are, but I do want you to notice that these are all very similar, right? They look similar because they are related. So we're going to start with weight of evidence. So, okay. So in the beginning, there's sort of like Bayes' rule. And Bayes' rule really is just a consequence of the product rule of probabilities. If the probability of A and B happening, I could write as the probability of A times the probability of B given A. I could also write as the probability of B times the probability of A given B. If I just divide those 2 things, I get Bayes' rule, the way that everybody talks about it. And this is really just, it's a consequence of what these symbols mean. What is conditional probability and joint probability mean? It means this. And because of what it means, interpreted as real numbers, if we compute this ratio of real numbers, we get this other thing. That's sort of all Bayes' rule says. The problem, the debate, all the interesting happens when we kind of replace A and B with 2 other letters, H and D. When we interpret this as a way of trying to assign probabilities for hypotheses, H, in light of data, D. And that's where all the frequentist versus Bayesian, all this philosophy, all the fighting, everything comes from. This sort of philosophical interpretation of a unimpeachable mathematical fact. well, so what does it actually mean? So if these terms, when we try to think about these random variables as being the random variable that our hypothesis is true, and D being that we observe some data, then this term on the left is the probability that the hypothesis is true after we observe the data. And that's a thing we would all like. That's a thing that I would like to say, right? That's what I should believe after invoking data. That's our sort of, quote unquote, posterior beliefs. This term would be the probability that the data happened if the hypothesis were true. This would be the probability that the hypothesis was true before we looked at the data. And this bottom term would be the probability of the data independent of the hypothesis. And so these are traditionally given names, right? Posterior probability of a hypothesis, the sort of likelihood of the data given the hypothesis, the prior probability of the hypothesis, and this bottom term I've most often seen called marginal likelihood. And this one's the tricky bit, right? I mean, this whole thing, sort of unimpeachable. We can assign this sort of philosophy to it. We can interpret these terms, and all that seems fine. But I really have a hard time thinking about what this marginal likelihood means, right? It's the probability of data independent of the hypothesis. And like, if I had a finite set of hypotheses, I might enumerate over them. But that's the tricky bit. So let's get rid of it. Let's consider not just one hypothesis, but two hypotheses. And let's take the ratio of these two equations. Once I do that, that probability of data term drops out as long as I'm using the same data to compare the two hypotheses. And so we end up with this simple relationship you might have seen before. The posterior odds of hypothesis 1 over hypothesis 2 is the prior odds of hypothesis 1 over hypothesis 2 multiplied by what's called the Bayes factor, which is the ratio of the likelihood of the data given the two hypotheses. And so this is saying, like, I don't have to worry about that tricky marginal likelihood bit. If I'm willing to just ask, here I have some prior beliefs, some prior probabilities assigned to hypotheses. Assuming I could compute this Bayes factor, I could use it as a multiplicative update for what my new belief should be in light of data. And we can make it even simpler. Instead of making it a multiplicative update, if we just take the log of both sides, we turn this into an additive update. This is the posterior log odds. This is the prior log odds. And this new term is the weight of evidence. This is what it is. This is where it comes from. Now we're going to talk about what it means. Weight of evidence is the log ratio of the probabilities of data under two hypotheses. And it is the thing that additively you add to your prior log odds to get your posterior log odds. If you don't know what odds, those are like betting odds, right? Like you go to the horse race, right? 3-to-1 against, 5-to-4, 4, I'm 20-to-1 odds, things like that. What does it actually mean? It's odds for a single event. It's a ratio of two probabilities. And so people normally talk about odds for a single event. And so the two events that they're considering is the probability that event A happens versus the probability that event A doesn't happen. And so in terms of a single probability, that's like the probability of A divided by 1 minus the probability of A. And so just a couple of simple illustrations. If you have a thing that happens with probability 1/2, we just throw in here, the odds of that are 1-to-1. The odds are 1, which we call 1-to-1, the even odds. If you had something that happened with probability 3/4, you stick it in here, the odds there are 3, which we could interpret as 3-to-1. What that's really saying is if there were 4 possible worlds, in 3 of them, the event would happen. So it is 3-to-1. There are 3 worlds where it happens versus 1 world where it doesn't. That's what odds are. More generally, it doesn't have to be the ratio of a probability of 1 minus the probability. It could be the ratio of any 2 probabilities. And then you're saying, given n worlds, in some fraction of them, the first thing happens, and the other fraction, the other thing happens. So this weight of evidence is actually kind of one of the first things that people ascribe the English word information to. So here's an excerpt of the Kohlbach's book about information, in which he identified this middle term, the information resulting from the observation X. He used X, we used D. We define the logarithm of the likelihood ratio. He used F's, we used this form, as the information in the data for the discrimination in favor of hypothesis 1 against hypothesis 2. Because Kohlbach, this identified what he thought of as, information, the English word information. What information is contained in data in favor of one hypothesis against another? And I'm having trouble following the comments that are going on. Oh, I'm breaking up. Okay, so let me try and turn off this background thingy.
So I think we mostly hear you well. It's just like from time to time there's like a small glitch. So
Well, I'll turn off the
Yeah,
fancy galaxy, and that might speed things up.
That's
So
very
it's,
understandable. Yeah.
What's the actual information that we're getting out of this communication channel?
Yeah, we need some better. Yeah. Okay. So weight of evidence. The log likelihood ratio is, what Kolbach identified as information. You should think of it as the information in some data in the favor of one hypothesis over another. So let's develop that notion a little bit more. I'm going to change notation here. I've been trying to use this sort of specific thing, talking about probabilities of events in light of some, other random variables. If we take those other random variables to be, oh man, my computer is starting to freeze up. Hopefully this doesn't happen for you guys too. To be a simple hypothesis, then we can write that as, the probability that the random variable x takes on the value little x, conditioned on the fact that some hypothesis p is true, I can write as p of x, the probability that the model p assigns to x. And similar, the probability that some event x takes on the value little x under the condition that hypothesis q is true, I can write as q of x. So I'm trying to turn this discussion about probabilities into just statements about probability densities. If we wanted to have a continuous random variable rather than a discrete one, we can do the same thing, but I just want to point out that it requires a little bit of care, in the sense that what we really might want to say is that some random variable x takes on a value between little x and little x plus some small interval dx under the hypothesis p. We could write as a density p of x times an interval dx. And we could turn a statement like this about the probability of random variables into a probability density. But independent of whether it's a continuous or a discrete random variable, the dx bit will cancel out. We can take the log of evidence for two simple hypotheses to just be the ratio of the probabilities. So if you observe x and you have hypothesis p, hypothesis q, the weight of evidence for p against q is log p of x over q of x. What units do we measure this thing in? So you could choose different bases for that logarithm. And historically, people used log base 2, and then the unit of weight of evidence was bits, or technically Shannons in the IEEE stuff. If you use base E, people call it a natural bit or natural unit. If you log base 10, a cute name is DIT for decimal bit, or it's also called a ban, or officially a Hartree. And historically, there's an interesting, if you do 1/10 of the log base 10 unit, so deciban for a tenth of a ban. Why is it called a ban? It's because one of the first people to talk about weight of evidence was actually Alan Turing, who with I.J. Good were working at Enigma machine. And so every day they would collect their transcriptions and stuff, and they try to figure out what configuration the Enigma machine was in that day. And they would work out their math on these large pieces of cardstock. The large pieces of cardstock were gotten from a town of Benisbarus. And so they measured the amount of evidence they had for the setting of the machine in the number of cards that they could generate, which they called bands, short for Benisbaruses. At one point, I.J. Good recommended that they measure things in tenths of cards because it might make the math more convenient. And so they measured most of their things in decibans. Decibans are much like decibels, right? In the rest of science, we call log ratios decibels, or they're usually measured in decibels, which is this 10 log 10 sort of unit. Apropos of nothing but useful for mental math, 2 to the 10 is roughly e to the 7, which is roughly 10 to the 3. Or you can write that in acute form. Log base 2 of x is roughly natural log of x plus log base 10 of x. It's useful for doing kind of conversions. Just to show you a simple example, bits in terms of nats, factor 1.44. You divide by the corresponding log, converting between bases. For the rest of this talk, not because other people do it, but because I think it's interesting, I'm going to do most of my units in decibands in reverence to Turing and I.J. Good. Okay, to give you some sense of how these things work, here are some decibands from 0 to 13.
Alex,
Here's the corresponding.
There was a question in chat about what happens if Q of x or P of x equals 0.
Oh, we will talk about that, but I think you can already interpret it from the formula, right? I mean, the weight of evidence goes to either infinity or negative infinity if P of x or Q of x is 0. What does that actually correspond to? If you have an event which is impossible under either hypothesis and you observe it, you can take that as strong evidence that the hypothesis is false. In fact, infinite evidence. But yeah, we'll talk more about that. So here's just a little table to give you some sense of how these things work. Here are some probabilities. Those are the things you're probably most familiar with. Here are the corresponding decibands from 0 to 13. Decibands, like decibels, it goes, every 3 decibands is a factor of 2. So every 3 decibands is 1 bit. So bits are sort of 1/3 of a deciband. Nats are, this other factor. Odds, somewhat intuitively, like 10 decibands is a 10-to-1 odds. 3 decibands is 2-to-1 odds. There's kind of these convenient ratios in between. A useful benchmark is, a lot of statistical science, which we owe to Fisher, sets a threshold for confidence at like 95% probability. 95% probability is 20-to-1 odds. That corresponds to 13 decibands. 10 for the factor of 10 and another 3 for a factor of 2. So I'm going to be doing things in decibands. The neat thing, I.J. Good claimed that 1 deciband corresponds to sort of just noticeable difference for human kind of perception of probability. 1 deciband is a 5 to 4 odds. And honestly, I think that's fairly good. Like if I was going to ask you very quickly to bet on like whether my birthday came from a month with 31 days, would you take that as a fair bet? Probably. That's actually sort of closer to 2 decibands than 1. Okay.
Can I ask a quick question just to form my intuition? So the bit, I wonder about how to intuitively think about the bit number and the probability.
Okay.
So is it intuitively correct to say that if I have, let's say, 2 bits, 0 and 1, and then the probability of each one of them, like the probability of 0 occurring is given by the last row, like 50% up to 95%. And then I want to find the minimum number of bits required to encode these. Then the second row, the bit number, is the number of extra bits that I need.
No, not quite. So here, these bits are weight of evidence. And in order to compare it to a probability, what I'm doing is I'm comparing it in the sense of the way odds are normally compared. So I'm looking at the probability of the event versus the probability of not the event. So I'm looking at P over 1 minus P. And literally the formula that's happening here is this log row is just log base 2 of P over 1 minus P. But the reason the logarithmic scale is interesting is because it's sort of more intuitive, right? Like the difference between 99% probability and 99.9% probability is very small in probability space, but that's actually fairly large. That's sort of 10 decibands in deciband space. And the measuring things in weight of evidence, so this logarithmic probability ratio space, is often much more intuitive, and it sort of corresponds to differences in the way that I think are more intuitive than looking at things in terms of probability, because those saturate and those are bounded. We will talk much more about coding and stuff later, but right now I just want to, it's really just sort of a new way to think about probabilities, a new parameterization of the space of probabilities. Okay. So what does it actually let you do? It lets you imagine sort of like
question?
Yeah.
Okay, so I think I'm missing something as well, because if you go back to the previous slide, so you say that 0 bits corresponds to odds of 1 to 1. So I guess I was thinking about this wrong, because the way I was trying to think, like make the correspondence between bits and odds is like if I have 2 hypotheses that are both equally likely, that's like 1 to 1 odds. But then if I tell you that one of them is true, I've given you 1 bit of information. But here it corresponds to 0. So I feel like that's the wrong correspondence that I'm trying to make. Can you tell me like where the misconception is?
So I think the best way to interpret that table is I was sort of interpreted as measuring in bits the log prior odds of a hypothesis against not the hypothesis. So it is just sort of the math that's happening.
Okay.
Perfect. Slide. If I had an event that had probability 1/2, the odds of that are 1. Log of 1 is, so measured in bits, I can either say I have an event that happens with probability 1/2, or in a different space, I could say that thing is an event that has probability of 0 bits. But I'm interpreting that 0 bits as a measure of the probability, as a measure of the log ratio of the event to not the event. It's a different space, right? There's a nonlinear transformation that I could use to go from probability space to this evidence space. And I just think the evidence space is sort of useful, given it's logarithmic and stuff. Things kind of move in intuitive ways. So we're going to work a bunch of examples now. So, but what you should picture is sort of this beliefometer in your head. 0 decibels, decibands of evidence corresponds to even odds. And then as you collect evidence, things can either kind of move left or right on the scale. And how far you go to the right is how strongly you believe in the thing. How far you go to the left is how strongly you disbelieve in the thing. As a simple example, imagine a loaded dice. We need 2 hypotheses. Let's take my first hypothesis, that the die is loaded, and it shows 6 1/3 of the time. So I've got a loaded dice versus a hypothesis that the dice is fair. So there's just like 2 hypotheses you're trying to compare in your head, and now we're going to talk about the weight of evidence, the log probability ratio as we observe events. So there's 2 classes of events. We could observe a 6. What happens if we observe a 6? We're going to compute the decibands. 10 log 10 of the probability that you get a 6 if the die was loaded versus the probability you get a 6 if the die was fair. If the die was loaded, the probability is 1/3. If the die is fair, the probability is 1/6. That's 2. 10 log 10 of 2 is 3 decibands. So there's 3 decibands of evidence. Every time, if you observe a 6, that provides 3 decibands of evidence. Your beliefometer should move 3 to the right for the thing being loaded versus it being fair. We observed either a 1, a 2, a 3, a 4, or a 5. Let's compute the weight of evidence. 10 log 10 of 2/3 if the thing was loaded, because we said it was 1/3 if it was a 6, and then we're going to split it between the other outcomes, versus 5/6 if it was fair. That ratio is 4/5. That's 1 deciband, roughly. So every time you observe a non-6, it moves 1 deciband to the left. Every time you observe a 3 decibands to the right. And we could use this to kind of update or tell us how strongly we should believe. What happens if we observe more than one outcome? Well, if we imagine that the events are independent, the neat thing about things being in this logarithmic space is we might have the probability of observing a whole bunch of dice throws divided by the probability of that same sequence of dice throws under the hypothesis. But if we're in log space and the events are independent, the probabilities factor and the logs add. So we can literally just add and subtract this weight of evidence as we make observations. So imagine we made a whole string of observations. Here's 20 rolls of the dice. And we saw 10 of them that were 6 and 10 of them that were non-6. Your little beliefometer is bouncing around every time you get an observation, but at the end of the day, we've moved to 3 decibands to the right 10 times. We've moved 1 deciband to the left 10 times. We are 20 decibands out. And so if you initially started with your prior belief in the ratio of these 2 things, if you thought it was 1-to-1 odds, I don't know, it's up in the air whether the thing was loaded or not, and we observed this sequence and we computed the weight of evidence, our beliefometer spun around, and we end up 20 decibands to the right, that's odds of 20-to-1, you should be sort of 95% sure that the dice is loaded. That's what we're doing. We're accumulating evidence for one hypothesis versus the other. And the weight of evidence is the log ratio of the probabilities. Why do we measure it in that way? Precisely because the log ratio of the probabilities allows us to just add and subtract the evidence as we make observations for independent events. So everything kind of like adds nicely. Let's do another example. Let's consider 2 hypotheses. Hypothesis 1, human births are 50% male, 50% female. Hypothesis 2, they're actually 51% male, 49% female. So this example actually goes back to Laplace. This is something that he wrote about in one of his first papers doing Bayesian inference. He looked at the Parisian birth records and between 1745 and 1770 and saw that there were 251,527 males and 241,945 females born. Let's compute the weight of evidence. Let's just add them up. The weight of evidence if you observe a male human birth for hypothesis 1 over hypothesis 2 is just this, 10 log 10, 51 over 50. The weight of evidence if you observe a female is 10 log 10, 40 over 50. And then add them up. Our beliefometer moves around. After all the observations, what happens? We are 404 decibans to the right. That is an astonishing amount of evidence. That is a probability of like 10 to the something ridiculous. I should have actually put it on the slide. You can be dead to right sure that the hypothesis that human births are 51% male versus 49% female, I think I screwed up the order here, is way, way, way more likely than their 50-50. Laplace concluded with the fraction is a little too great, and it's also of excessive smallness we can regard as certain as any other moral truth that the difference observed in Paris between birth of boys and girls is due to a greater possibility of the birth of boys. You can be dead to rights, sure than you are probably most sure of things in your life, that human births are more male than female.
Just want to jump in here to, I think this is also one of the areas where things get confusing sometimes for people, is the H has the assumptions about what is included. You've compared these two in the context of, Paris between 1745 and 1770. And so there's always the question of all the other hypotheses and data that are outside of that conditions. And so that's always something that comes back, and like, are you considering the full hypothesis space and the full data, right?
No, yes, thank you. All we can do is right now we're comparing the weight of one hypothesis over another. But you can be dead to right sure that hypothesis 2 is much more likely than hypothesis 1. But adding more hypotheses, things get more complicated.
Yeah, I just want
let's do.
Shut up.
Yeah.
I'm sorry, one more question.
Yeah.
So you could also do the calculation just by calculating the likelihood of the observations under hypothesis 1 and hypothesis 2, and you're saying that would give the same answer, right? Like this is just another way to do that calculation.
Yeah, it's another way to think about it, and it's another way to put it on this other scale, basically. I mean, we're not doing anything new, right? This is equivalent.
Yeah.
So what Laplace actually did was computed the posterior probability sort of the hypotheses under the thing, and he worked out all the stuff. But just if sort of a simpler thing, if we have two hypotheses that we want to compare, we compute the weight of evidence of the observations, we can add or subtract them, and we can ask just how much does the belief-o-meter move? And in this case, it moves 404 decibands towards 5149, away from 50-50.
Except there's this one point that you made, Alex, right? Which is that if you actually wanted to separately compute the likelihoods, you'd have to try to understand that likelihood of data term. So I mean, so like that's one of the.
No, but that's why it's beautiful. As soon as we only compare two hypotheses, we don't have to worry about the likelihood of data. Yeah, you're right. Thank you, Ethan. It would be harder to do what Vinay just asked, and that's why I'm not doing it. Instead, we're just comparing two hypotheses, and things get nice. Well, so it does ignore the prior term, but we'll talk about that now, right? In the sense that this tells us how much we should move. It doesn't tell us where we should start. You get to start wherever you want. And I think we can illustrate that with like a COVID example. Imagine here's one hypothesis, you have COVID. Another hypothesis, you don't have COVID. And what's the data going to be? You're going to take a COVID test. And the COVID test is either positive or negative. What's the weight of evidence if you get a positive test? Well, what we would need to know is the probability that you get a positive test if you have COVID. And that's the sensitivity of the test. And the probability that you test if you don't have COVID, which is the false positive rate of the test. The log ratio of those two things for some tests I looked up, 13 decibands that you would get for every positive test. What about a negative test? We need to know the probability that you get a negative result if you have COVID. That's the false negative rate. What's the probability of a negative test if you don't have COVID? That's the true negative rate. Log thing, negative 12 decibands. Like Ben said, importantly, you take the weight of evidence and you add it to your prior log odds. So in this example, if you started with even odds, if you started at 0 decibands for your prior belief in whether you had COVID or not, and you get back the one positive test, you move, You move 13 decibands to the right, and you'd end up over here, kind of on the far end of your belief-o-meter, greater than 21 odds, you probably have COVID. But if you started with a relatively rare chance, 20 to 1 against that you had COVID, you think 1% chance you do have COVID. You still, using the exact same weight of evidence, move 13 decibands to the right, and you're sitting at something like 1 or 2 decibands, just noticeably different change in your probability that you have COVID over even. So weight of evidence, yeah.
Question about this. This came up with Elon Musk recently. So if you had like symptoms, like you had coughing and fever and that type of stuff, and then you take a test, does that do we think of that in terms of affecting the prior, or should that be affecting like a conditional? I mean, I guess the test still has the same false positive and negative rate, regardless of whether you have symptoms. I guess how does that?
The beauty of talking about weight of evidence is independent of any of that, right? The thing that is sort of unimpeachably true is, in so much as these false positive and true positive rates are correct, this is the weight of evidence once you get the positive test. Now, we could do the same calculus and we could estimate what's the weight of evidence if I have a runny nose. And I could try to compute the probability that I have a runny nose if I do have COVID versus the probability of I have a runny nose if I don't have COVID. And that would just give me another update to the belief-o-meter, right? I don't need to say that that's a prior. I could say that that's just a different update, a different piece of evidence, and a different amount of weight that I add or subtract to my belief-o-meter. And that's, I think, part of the beauty of thinking about things on this scale is the dial just moves. A new piece of evidence, I have a runny nose. Oh, that probably moves it a little bit this way. I get a test. Apparently that moves it 13.
Alex.
Oh, you know, I had a negative test yesterday. That probably moves it all the way this way.
Question. So that the example I guess we just talked about with like the symptoms and the test and so on, there's an implicit or there's a very or explicit assumption here that those two things, the like let's say the symptoms showing and the testing and the test being positive are uncorrelated, like they're independent events. Otherwise, you can't naively add them up unless one of these left-hand or right-hand side conditionals needs to be does have COVID, comma symptoms. Sorry, does that make sense? I guess like if you want to
you're only allowed to add them. They only add if they're independent, and that's precisely because then the probability that both happen factors. If things have correlations, you can still compute the weight of evidence. You just have to do it jointly. You would have to compute the probability that you have a positive test and you have a runny nose if those two things were correlated, given that you have COVID, versus the probability that you have a positive test if you don't have COVID. And you need to do that jointly. But you can still use the sort of weight of evidence framework or whatever.
Sorry for getting a little off track, but I guess I'm curious what happens in a situation where the measurements are biased by that. So let's say the majority of the tests are only taken by people that actually, have symptoms or something like that. So you don't have good data, so that you don't have good data for coverage of the cases where people don't have symptoms. Let's say.
I mean, that I think could go into affecting how you estimate these probabilities. Right? In the sense that that could affect your inference for what the true positive and true negative rate of the test is. But I don't think that affects your own weight of evidence, like directly, in the sense that all it does is indirectly affect what you think these probabilities are.
I see. Yeah. Okay. Yeah, I got it. Thanks.
As a simple continuous example, let's say we had two hypotheses, the blue Gaussian and the orange Gaussian. What's the weight of evidence? It's the log ratio of the two probabilities. In this case, it looks like a sort of straight line on this logarithmic scale. And so what is this saying? This is saying if I observe an outcome over here, I accumulate 13 decibands of evidence that it came from orange rather than blue. Because over here, orange has density, blue has very little density. If I were to make an observation over here, I accumulate 13 in favor of blue against orange, because blue has way more mass over there than orange does. Somewhere right in the middle between the two, I accumulate no evidence for either hypothesis over one another, because the models don't have any preference either way. The odds are the same. They're even odds at that point, to kind of give a visual representation. As the next example, let's consider M&Ms. So fun fact, M&Ms come from two factories, and the two factories have a different distribution of colors. There's a factory in Hackettstown, New Jersey, and a factory in Cleveland, Ohio, and they produce M&Ms in different ratios. So we can compute the weight of evidence. I pull an M&M out of a bag, and it happens to have a certain color. What's the weight of evidence that it came from New Jersey versus Ohio? Here they are for each individual color. The most distinguishing color is green. If I pull out a green M&M, I actually get 2 decibands of evidence that it came from Ohio rather than it came from New Jersey, because Ohio produces green M&Ms nearly 20% of the time, but New Jersey only produces them 12% of the time. Meanwhile, if I were to pull out an orange one or a blue one or a brown one, I actually accumulate some evidence that it came from New Jersey rather than Ohio. I could open a bag of M&Ms, I could go through them one by one, I could move my belief-o-meter, and I could see where I end up, and that would tell me how much I should move my prior belief that that bag came from either New Jersey or Ohio. I think this sort of raises an interesting question. How likely am I to be able to tell whether my bag of M&Ms came from New Jersey or Ohio? Let's say I don't have a bag of M&Ms in front of me. I'm sorry?
Can we maybe talk a little bit about the independence assumption in this example? Because is it like the factory flips a coin and I'm going to spit out this color, or You know, like why is it a reasonable assumption when I pull an M&M out that, you know, I can just add the odds?
You could, I think it's a reasonable assumption that a bag of M&Ms is a well-mixed selection of independently produced streams of M&Ms.
Mm-hmm.
Right.
I see.
I think what's going on here is they have sort of like twice as many orange and blue machines, or machines set on the orange and blue setting in New Jersey than they do in the other ones. And I think what happened in Ohio is they had some degradation in the machines, and some of them run faster or slower than others. I'm guessing. But my picture is that each machines are producing these M&Ms. They're dumping almost a conveyor belt. The conveyor belt gets scoop up some of them and throw them in a bag. And so I think it's fair to assume that the individual M&Ms are sort of independently drawn from two categorical distributions. But that is what I'm assuming. And so what I could do is I could go through each of the M&Ms and I could accumulate my evidence. I could move my belief-o-meter for whether it came from New Jersey or Ohio. But now I could ask a very interesting question. Should we expect to be able to tell whether it came from New Jersey or Ohio? So what if we asked, in expectation, if I actually had a Jersey bag, how likely am I how much evidence am I expected to accumulate in favor of New Jersey against Ohio if I have a New Jersey bag? Or how much evidence am I likely to accumulate in favor of Ohio versus New Jersey if I actually have an Ohio bag? And that's actually relative entropy, or KL diversity.
So, sorry, doesn't this depend on, like, don't we need to have knowledge about how much M&M each factory produces?
Yes.
Like, okay.
Well, not how much they produce overall, but we need to know how many were in a bag, right? If we were going to try to answer the question of how much evidence we expect to accumulate in a given bag.
But even how much they produce overall, right? If Ohio factory produces too much is more like M&M bags, then each bag is more likely to have come from Ohio even without any observation, right?
I mean, that's true. So that could set your prior belief that the bag came from Ohio versus New Jersey, but you can still do this belief-o-meter update, and we can still ask the question, how much evidence should I expect to accumulate from a New Jersey bag? How much evidence would I expect to accumulate from an Ohio bag?
Yeah, correct. What I'm saying is that to answer that question, we would need that knowledge, right? Because if, for example, Ohio
not to answer the update, we don't need to know the prior in order to figure out how much our belief-o-meter will move. But that will affect how much our final belief will be.
But in order to know how much movement we need to decide where the M&M comes, that depends on the prior, right? Yeah.
That is true. That is true. That is true.
Okay.
So this gives us our first interpretation of several interpretations for what relative entropy is. Relative entropy is an expected weight of evidence. That's what it is. It's a way to try to compare two probability distributions independent of data. And remove the data dependence is we generate data from one of the two hypotheses. This was the weight of evidence in favor of P against Q, and we could compute that with respect to some data. But if we want to remove the data dependence and only talk about two distributions, we can choose to generate data from one of the two hypotheses. The choice of which may or may not be important, but it's a choice we have to make. Conventionally, when we write relative entropy or KL divergence from P to Q, we draw the data from P. And the relative entropy is what is the expected weight of evidence in favor of P against Q in observing observations from P in expectation per observation.
Alex, maybe you
write this. Yeah.
Maybe you already answered this a second ago, but do you happen to know what fraction of M&Ms are made in each factory?
I don't. Sorry, you have to. You're on your own for your prior. Unfortunately, I have no evidence or data. Just some notation to run through. We can write this like this as an expectation. For a discrete thing, it becomes a sum, right? A weighted sum. For a continuous thing, it's an integral. And I personally like writing things with brackets because they're perhaps cleaner. So what is it for our M&Ms? We can just do it, right? We had our weight of evidence per M&M color, and now you can just kind of like compute the weighted average of this, taking weights from New Jersey or taking weights from Ohio. And what do you get? The expectation, the New Jersey expectation, is 0.108 decibands in favor of New Jersey. The expected weight of evidence, if you weight it with the Ohio probabilities, is actually minus 0.117 decibands in favor of New Jersey, aka 0.117 decibands in favor of Ohio. If we have an Ohio bag, we can expect to accumulate evidence in favor of Ohio. If we have a New Jersey bag, we can expect to accumulate evidence in favor of New Jersey. The KL divergence between this categorical distribution and this categorical distribution is the expected weight of evidence you would accumulate that the bag is from New Jersey over Ohio using a New Jersey bag. The KL divergence from Ohio to New Jersey is the expected weight of evidence you'd accumulate in favor of Ohio against New Jersey using an Ohio bag. And they are not the same. They're asymmetric. But I'm really hoping that that starts to make sense. They're asymmetric because they're asymmetric. They're asymmetric because they're different distributions. These different colors had some fixed weights. We noticed that like green was particularly discerning. But green is particularly discerning. Why? Because Ohio produces more greens than New Jersey. But for the same reason, if I had an Ohio bag, I'm going to see more greens than if I had a New Jersey bag. And that's going to accumulate more to the expected weight of evidence. And so I shouldn't expect that these are being the same, because I shouldn't expect that two different weighted combinations of these variables or vectors are going to give me the same answer.
So,
Scale divergence is asymmetric. Yeah.
Alex, can you kind of help me understand how did you get 0.108? So we sampled to calculate E New Jersey, we sampled from New Jersey data and calculate the weight of evidence. Is that what we did?
Yeah. So I guess to talk through this whole table, right? What is 0.035? It is 10 log 10 of 12.5 divided by 12.4. What is negative 0.2? It is 10 log 10 of 12.5 divided by 13. What is this 2? It's 10 log 10 of 12.5 divided by 19.8. And then how would I get this number, 0.108? I'm going to take the expected weight of evidence. So I'm going to take 12.5% times 0.035 plus 12.5% times negative 0.2 times 12.5% times negative 0.33 times 12.5% negative 2, 25% 0.86, etc. And how am I going to get this negative 117? I'm going to do the same thing, but using the Ohio numbers. I'm going to take the weighted sum of the weight of evidence. The KL, by convention, kind of reverses the thing. And so when we wrote the weight of evidence as New Jersey over Ohio. So when we take the expectation with respect to Ohio, we got a negative number, meaning it should push us in the Ohio direction. When we write the KL, the convention is that it's with respect to the first argument. That means that we should actually reverse. If for computing the KL, these numbers all get multiplied by -1 because we're interested in Ohio over New Jersey rather than New Jersey over Ohio. Did that help?
Yeah, definitely. Cool. Thanks.
And we can actually simulate things. So
one more quick question. This is per M&M, right? Like each M&M gives you on average 0.108.
Each M&M gives you this, and yeah, the expectation is in expectation. What would each M&M do? And that is very prescient, Vinay, because here's some simulations, right? If we actually had bags of M&Ms and these things actually were categorical distributions, we actually sampled things, then your beliefometer undergoes some stochastic walk. What happens if we have New Jersey bags? Here's a simulation of, I think, 100 different New Jersey bag runs, each blue curve, the weightometer, the beliefometer movement. If we had an Ohio bag, we have all these different orange things. But in expectation, they look like a line. Because in expectation, every M&M provides an expected amount of evidence. And we accumulate evidence at that rate. So relative entropy is asymmetric. And I think in a lot, this is ordinarily somewhat of a mystery, but hopefully this way of thinking about things can clarify why it shouldn't. Okay. Let's talk about, so the next interpretation of KL divergence that we're going to talk about, which is related, but I think somewhat distinct, is you can think about relative entropy as a measure of how large of an update there is in your beliefs. It was a number that we used to compare two probability distributions. And let's imagine you start with some distribution, P, or you start with some distribution Q, and then you update your beliefs to some other distribution P. We want a number that measures how large of an update that is. How much has your opinion moved? How much has your opinion changed? How large of a change was that in your beliefs? So imagine we revisit that COVID example. We talked about two random variables. You have or have not COVID. You did or did not get a positive test. That's 4 possible outcomes, and you could assign some probability on that space of 4 possible outcomes. Let's say it's this one, 6%, 0.4%, 4%, 89%. here's a different probability on those 4 outcomes. And let's say you did something and you changed. You went from this belief to this belief. How big of a change is that? What we want is a way to measure the bigness of that change. So I want to take a break for a few minutes, but I want you to think about that. What properties should that update have? If you're just thinking about what would I want, like if I wanted to assign a number to the magnitude of your belief update, what properties should that number have, that function have? And let's talk about it. Let's all take a break. Let's like concretely make it for 5 minutes, and then we'll come back and we'll keep going. I'll try and, I haven't been looking at the chat. I'll try and answer some questions or whatever, but let's take a little break. Okay, so I'll answer people's questions. We won't start again until we said like 3 after, but if people want to ask questions to it, I just had to use the restroom. So. Yeah, I mean, the real thing, just, you know, fun fact, if you actually look at the serial number on the M&M Bigs, it'll tell you whether it's from New Jersey or Ohio, but that's not new. Yeah, so sorry, yeah, Oscar, D is for disease, T is for test. And then the bars meant not disease, not test. No worries. I mean, yeah, if you guys really, if you have a pressing question, feel free to just like, you know, mic in, because I'm trying to like look at the thingy, but it's hard, you know.
Alex Urban asked
There was
an
a-
interesting question.
Oh, Ben had an interesting question.
No, Alex Urban did in chat.
Oh, yeah, I saw him ask. Okay, this is a general statement about computing. We don't know which hypothesis. Wait, this is a general statement about comparing 2 hypotheses, but we don't know which hypothesis we're actually sampling from. Right? Yes. So, oh yes. So yes. So hopefully that was clarified a little bit. But when we were first talking about weight of evidence is, you know, it takes 3 things. You need data and you need 2 hypotheses, and they're kind of associated probability distributions. But that data comes from anywhere. It could come from those hypotheses, or it could come from some other thing entirely. It could come from the real world. It doesn't have to come from either of the hypotheses. The weight of evidence just now tells you, it gives you the weight of evidence, the information you have in favor of the hypothesis over the other, given the data. And then what we've done now is we've removed that data requirement, in the sense that we don't need an independent source of data. If we really wanted a way to talk about 2 probability distributions, we could simulate the data from one of the 2 distributions. And that's what relative entropy is. That's what KL is. So
Okay.
yeah, hopefully that addresses, yeah. Was that you?
Yeah,
Alex?
thanks.
There
Yeah,
was another
that's me.
question about what to do if you have 3 hypotheses. So can you do it better than
Oh, yeah, I
just
saw that.
pairwise
So-
belief meters?
I don't, I don't know. I mean, you could certainly do the pairwise comparisons. And I think those are the only things that are sort of clear, and those are the things that are going to be elegant. Now, that isn't the answer that you want, but in order to answer the kinds of things that you want, like assigning actual probabilities to one of 3 hypotheses, eventually you're going to have to compute one of these like marginal likelihoods. Now, you could do that if you're willing to kind of compute some marginal likelihoods or something, but I think that's I think that's the reason why all we ever do are binary hypothesis testings in practice. But I think you can still build a lot of, you can do one versus rest. That's true. If you have so that's a common thing, is if you've got a finite set of hypotheses, you can either do one versus rest, or you can do one versus all even, honestly. And then the probability that your data came from a hypothesis, if you have an exhaustive set of hypotheses, is 1, and things kind of simplify. And that's an exercise I should put on the problem set, but maybe I'll add.
So Alex, I have like a question. You said that you got the related entropy by removing the dependence on data, but still to kind of calculate the expected values, you still need to kind of sample the data from a distribution, right? And from one of the hypotheses. So technically, you still have the dependence on data, right?
I guess not from an external source. So this goes to what Alex was saying, or Alex Erpong, right? In the sense that for weight of evidence, what I envision is I have the 2 hypotheses and I collect data from like the world, and I don't know where that came from. I mean, it realistically probably didn't come from either one of my 2 hypotheses, right? It's actual data that I collected by some other process. Now, in the kind of relative entropy sense, I don't need to go and collect data. I can simulate it, right? So I meant it removes the dependence on some external or some independent data that I need to use to update my beliefometer. I can ask a sort of theoretical question. If I generated data from P, if I generated data from Q, how much would I expect my beliefometer to move?
Got it.
Okay, so we have officially ended the time of things. Yep, so Vinay kind of worked it out. Well, so 20 decibels of evidence is, 101 ratio if you had 200 M&Ms. Yep, so with a 200 M&M bag, the smallest bags are about 56 M&Ms. Just FYI. Okay, so I invited you in this break to kind of think about the next interpretation of KL. So also just a note, we didn't quite get as far as I hoped before the break. We've got sort of half an hour left. I'm going to kind of do things. Anything that we don't cover, we could cover next time. At this point, we've done most of the work. So I really wanted to spend a lot of time, get very intimate with weight of evidence and sort of that interpretation of relative entropy. Now what we're going to do is we're going to try to build up a whole bunch of other interpretations that are all related and hopefully view them through the lens of weight of evidence and kind of get through relative entropy, maybe talk about entropy and mutual information. Again, if we don't get through it, we can kind of talk about it at the beginning of next time, or we could not, depending on what you guys say. But I guess I want to focus more on kind of like building the intuition. And so if we run out of time, we run out of time. But feel free to. Yeah. Okay, let's talk about this next thing. I had some belief, and I changed my belief, and I want to talk about how much my belief changed. What properties should the change in belief function have? Well, I don't know, but well, I'll tell you. Relative entropy, I think, is a good way of measuring updates in change of belief. So what properties do you want to have? It seems reasonable it should be continuous. Continuous in the sense that if I made a very slight perturbation to one of the 2 beliefs, I would expect a relatively small perturbation in the change in the update between the beliefs. If I changed New Jersey to be 2426 instead of 2525, and I asked for what happens if I change my belief distribution from New Jersey to Ohio, how big of a change that is, or from Ohio to New Jersey, I would want it to be a small change. Small changes in the distribution should be small changes in the magnitude of the update. And that's true for our function KL. Small perturbations to either one of the distributions is a small perturbation in the relative entropy. We would want it to be reparameterization independent. And I mean that kind of in 2 senses. One, we would want it to be permutation independent, sort of trivially. Like whatever formula we use, it shouldn't matter. Here I actually changed the order of the colors and the order of this table. And whatever like mathematical formula I use, it shouldn't matter like what order the vector is in. I should get the same answer, right? Because we're talking about updates of belief. It shouldn't matter like the order in which I place the states of the belief. It should be independent of that. And our formula for KL is manifestly permutation invariant because it's a sum, so permutation invariant. If I permute every term in the sum the same way, I get the same total. It's also, we would also want our belief update function to be reparameterization independent in a broader sense. Like if I change, a coordinate system, I wouldn't want that to affect the answer, right? If I had some probability distribution in this space, in this room, about like where my head was going to be, I could write that in like Cartesian coordinates. I could have 2 different beliefs about where my head's going to be, and I could write both of those in Cartesian coordinates, or I could write them in like polar coordinates or spherical coordinates, and like that shouldn't matter. That shouldn't change the answer. And relative entropy is that. It's independent of that kind of reparameterization as well. And I don't want to belabor this, but sort of the math works out in the sense that if I had a coordinate change from some coordinate system X to some other coordinate system Y, how does the probability change? Well, the density should be like, it doesn't matter how you slice it, density would stay the same. So how do you compute the update to a density? The density in any small region should be the same before and after the update. And so the probability, the new probability distribution can be written as the old probability distribution and then times a dx dy, which is like a Jacobian. So you get these Jacobian factors that end up. And because we had this log ratio, that Jacobian term cancels out. And the formula for KL divergence or relative entropy is reparameterization independent. I don't want to belabor that, but I want you to believe me that a proper update in our belief function should be parameterization independent, and also believe me that our relative entropy formula is. You'd also want it to be non-negative, right? If we want to describe how much your beliefs change, it doesn't feel like you should be able to have negative changes. And our relative entropy function is positive. This is a very useful property. Now, in our other interpretation, as expected weight of evidence, this makes sense, and this has a very nice intuition. Expected weight of evidence being positive means if you accumulate data in expectation, data from the correct hypothesis will move you towards the truth. A New Jersey bag will convince you it's New Jersey over Ohio. An Ohio bag will convince you it's Ohio over New Jersey. If it wasn't positive, that wouldn't be the case. You could draw data from the distribution and move away from it being the thing that you prefer. Relative entropy doesn't have that property. In the process of in your change of beliefs, you would want, if I go from any distribution to any other distribution, it should be some change, and zero change we would like to correspond to no change. Relative entropy has these properties. Here, the math, again, I don't want to belabor, but it is simple enough that I think just showing it, you could reconstruct it afterwards. And what's one way to do it? A simple way to do it is actually to use the fact that we can, bound the logarithm. So here's log of x. If I draw a straight line, log of x is always below that orange line. That orange line is x minus 1. So log of x is always less than x minus 1. It's just math fact. But we can use that math fact in order to get a bound on relative entropy. Because we can write out relative entropy. I'm going to swap a minus sign, flop the log. I'm going to use this bound. And then I'm going to pull the thing apart. And we end up with a thing that looks like the integral of q everywhere. Q is a distribution, so it integrates to 1. The integral of p everywhere. P is a distribution, it integrates to 1. We end up with minus 1 plus 1. Last I checked, that's 0. Relative entropy has to be positive. And this makes sense. This makes sense both as an expected weight of evidence and as some measure of updates in belief. Also, from this proof, it makes clear, when is this equal 0? When is this thing tight? It's tight when this approximation is tight, and this approximation is tight when x equals 1, or when p equals q. So KL divergence, relative entropy, is non-negative, and it's only 0 if p equals q, if the two distributions are the same. If the two distributions are the same, then you accumulate evidence. It's not going to push you in any direction. In expectation, it shouldn't move your beliefs. If you move from q to p and q is p, then you shouldn't have moved anywhere. So as a measure of update in belief, it should be 0. Here, I wanted to talk about the edges. So, what does this function behave like in the limit? I think Ethan asked this much earlier, but in the limit that either p or q is 0. Once we look at relative entropy, this thing is an expectation. So inside of there, it has a thing which is like p log p. So the question is, what does p log p, or what does x log x look like in its limits? Well, here's a plot of x log x. As x goes to infinity, the thing goes to infinity. But as the thing goes to 0, what is it? It's hard to tell from the formula. It's easy to tell from the plot. If the limit is x goes to 0, x log x goes to 0. So it's well behaved. The other piece of it looks like log q, or minus q. What does that look like in the limit as x goes to 0, as x goes to infinity? Log x goes to infinity as x goes to infinity. And as it goes to 0, it goes to negative infinity. And so what does this say? This says that our formula for relative entropy, what is it going to behave like? Well, we're going to have a real problem if we try to set, so p can be 0 anywhere, because p log p is 0, and that's not a problem. P can be 0 anywhere. Your new beliefs, the ones that you update to, the ones that you're drawing data from, can be 0 someplace, and you're not going to have a problem, because you're never going to see them. If New Jersey never produced blue M&Ms and only Ohio did, that doesn't matter, because once we draw bags from New Jersey, we never see blue M&Ms. But if Q was 0, someplace P wasn't, that's sort of a problem, right? The formula blows up. But this makes sense too. If New Jersey produced blue M&Ms and Ohio didn't, and we saw a blue M&M, then we can be dead to rights sure it wasn't Ohio. And that's what's happening here. I don't think that was a good
I
description.
think there's a typo on this slide, right? Last sentence, Q cannot be 0 where P is not 0, right?
Yes, thank you. Thank you. If we're going back to this intuition about how much we update our beliefs, it's hard to talk about what it should be in general, but for uniform distributions, I feel like I have an intuition. Like, let's say I'm playing like Guess Who, or I'm playing, one of these guessing games, and I don't know which of the kind of 32 characters it is. And if I change my belief from being uniform on 32 people to getting a question right, or getting an answer and being uniform on 14 people, I feel like going from 32 to 14 should be a smaller change in my belief than going from 32 to 3. I would want this function to be monotonic in that sense. If I go from a large population I'm uncertain about to a small population to a smaller population, the magnitude should be kind of monotonic in the size of the shrinkage. And our formula does that. If we have two uniform populations, 1 over n things, and then new 1 over n prime things, formula is just the log of the ratio of n to n prime. So, like, let's say it's 2. Let's say I cut a space in half. I had a uniform distribution over n things, and I cut it in half. That's 1 bit, or 3 decibands. So any well-chosen yes or no question that cuts the space in half, that changes your belief by a factor of 2, is sort of 1 bit of update, 1 bit in magnitude of your change in belief. So this gives you another interpretation. You can interpret the KL divergence as sort of the number of optimally designed yes or no questions that would move your beliefs from Q to P for any Q and P. And then the last property that we would want, chain rule. So what do I mean by this? Basically, like, there are different ways that I can write probability distributions, and where I would want my description of updates and changes of beliefs to be consistent, independent of the way that I write those updates. So let's go back to our COVID example. D is disease, T is test. I have 4 possibilities. Yes, I have the disease and I got a positive test. Yes, I had the disease, I got a negative test. I don't have the disease with a positive test, and I don't have the disease with a negative test. And I could write a distribution over these 4 things. Let's say I start with this blue distribution, and then I update to this orange distribution. That's just the thing I could do, right? There are 2 different distributions on these 4 things. And I want to calculate how big of an update did I go from blue to orange. Now, the point is, this blue distribution is equivalent to this blue distribution, right? I could think about the problem differently. Instead of just being a distribution over 4 possible things, I could think about it as, first I decide whether or not I have the disease, and then conditioned on whether or not I have the disease, I decide on whether or not the test is positive. And this distribution, these numbers, like, this is an equivalent probability distribution. This is an equivalent set of beliefs, this blue to this blue. Similarly, this orange is equivalent to this set of orange numbers. And I would want, for any function that measures how much I move when I move from one distribution to another, like, I should get the same answer whether I calculate in these diagrams or in these diagrams. It shouldn't matter, because those are equivalent ways of, those are, independent ways of describing the same sets of beliefs. And our function, relative entropy, does do that. It decomposes in this natural way. So, like, to actually, like, do the math, if you just take these 2 diagrams and you run the numbers, you get a certain number for the magnitude of the updated belief, the relative entropy. And in this case, it's 9.7 decibands. And then if you do it for these things, what you have to consider is, first, we've got this first level decision, D or not D. And so there's these 2 Bernoulli distributions, 97 to 7% versus 38 to 61%. What's the formula in that case? 4 decibands. And then I've got this little binary decision, 93.8% versus 100, right? What's that in that case? 28 decibands. That's a small update, right? It goes from, 93 to 100. And then I've got this last branch. I go from 4% to 100%. That's a big update. That's 13 decibands. What does our relative entropy do? How do we turn these 3 numbers into that number? You take the weighted average, and you weight them according to your new beliefs. So you take this first number, 4 decibands, and then you take 61% of this number, 28 decibands, and 38% of the difference on this branch, 13 decibands. You add those all up, you get 9.7, the same as we got in the first case. So the relative entropy sort of decomposes. It satisfies this chain rule even when we break up the probability distribution into different pieces. And the chain rule, the way that you combine the pieces, is just additive. I don't think I want to talk about this. Mathematically, I don't want to belabor it, but if you just write out the formula and you pull the pieces apart, you could see it. You write out the log of the joint, you write the joint as the product, you get this log of this product, and that splits into pieces. And then each one of those pieces looks like a KL. That's why it happens. But there's a plus here. It's additive, right? It's a weighted average. It's not a multiplication. It's not some convex function. It's just adding. The neat thing is, we just described some properties we might want some measure of an update of belief to have. The relative entropy, this function that we talked about and we described as expected weight of evidence, turns out to be the only function that satisfies these properties, like axiomatically. And that's just kind of a fun fact. So there's this cool paper by Arthur Hobson, and it shows that the only function that is continuous in the probability distributions, reparameterization independent, non-negative, monotonic for uniform distributions, and satisfies a natural additive chain rule, the only function that does this is this P log P over Q function. So that gives us another way, another peg to hang our hat on. What is KL? It's the only function that does this. And why is these properties useful? This is what we decided over break might be reasonable properties for a measure of the magnitude of the update of our beliefs to have. Okay, the last interpretation I want to leave you with for KL divergence is it's a measure of like a distance between two probability distributions. And that's very close to the rate of what we were just talking about, a magnitude of the update beliefs versus sort of a distance. And I guess, yeah, I don't know if this is quite related, but okay. Another interpretation I want to give you is that KL divergence, you can, like, how do we actually interpret the number, right? We get these numbers out. We can measure them in bits or nats or decibands or whatever, but what does the actual number mean? Well, we could think about it as, since it was an expected weight of evidence on a single observation, we could turn that into a question of like, how many observations would I need before I could be convinced that P was true over Q, right? So if the relative entropy was the expected weight of evidence in a single observation, and before in our table we decided that 13 decibands, aka 3 nats, if you do the conversion, of evidence was 20-to-1 odds, and we were like okay with that being a nice threshold, we could ask, like, how many effective measurements would we need before I accumulate 3 nats of evidence or 20 decibands of evidence or 13 decibands of evidence in favor of P over Q? Because we know that it's going to be positive. We know that if I draw things from P, I will favor P over Q. But how many samples do I need before I can be sort of like, Fisher certain, 95% certain that P is true over Q? And so you could just do this kind of calculus and get the effective number. So I want to talk about the birth example we talked about before, right? If you take Parisian births for 4 years, we accumulated 400 decibands, like a tremendous amount of evidence that human births are much more likely 51-49 than they were 50-50. And like, this is weird to me because it seems almost paradoxical. I think most people, I mean, you might have heard that in school. Also, it's true. Like it works in every country across time every year. More males are born, human males are born than females. Just fact. But that's something that I feel like most people don't know if they weren't told it in school. And they walk around thinking human births are 50-50 male and female. And like, how is that consistent? There's a tremendous amount of evidence that that's not the case. And yet people believe it, and they sort of like don't make mistakes, right? Like I didn't I feel like not knowing that fact wasn't hurting me. Well, how could that be? So if you compute the KL divergence between these two distributions, 51-49 to 50-50, we just do P log P over Q for those two things. It's 870 nanidecibands. Like that's a terrible SI unit, but 870 times 10 to the minus 9 decibands is the expected weight of evidence in favor of 51-49 over 50-50. Those two distributions are very close in any sense of the word. Those are nearly the same distribution. How many measurements would you need in order to accumulate 3 nats? 15,000. And now we resolve the paradox. As an individual, I don't think I have observed, I'm not personally aware. I have 2 kids. I don't have 15,000 kids. And so like, I haven't been, I can't accumulate even all my cousins, all my nieces and nephews, several dozen, but I don't know 15,000 children. And so I've never been able to accumulate enough evidence to sort of reject the hypothesis that human births are 50-50. But as soon as I look at even like Paris in the 1700s for 5 years, there's 100,000 births, 500,000 births. That can totally be enough evidence that you could be morally certain that human births are 5149 versus 50-50. And we can actually interpret this number, 870 10 to the minus 9 decibands, as like a measure of how many births I would need to observe or be familiar with before I would start to feel that they were different. I could feel as if, males were more likely born than females.
Sorry, I have a question here. So this works. Oh, sorry. So this calculation works if we know that the data comes from either P or Q, right?
Yes.
So for the birth case,
weight of evidence works even if the data doesn't come from P or Q, but it answers a very specific question: how much you should favor P over Q in light of the data. The Kale divergence asks how much you would expect the weight of evidence to change if you drew the data from P or Q.
How much you would expect the weight of evidence to change?
So in this particular case, I am I didn't actually, the formula is wrong. I needed to have a factor of 0.51 or 0.49 in each term, or 0.50 or 0.50 in each term. This in particular case, it's supposed to be 0.51 and 0.49 in each term, right? It's formula's wrong. But why did I do it that way? Does it really matter if I don't? It's asymmetric. It's not particularly asymmetric. You could do it yourself. But what I'm asking here is, let's say the world is 5149. How many births would I need to observe in a 5149 world before I could accumulate 3 nats or 13 decibands of evidence in favor of a 5149 world versus a 50-50 world?
right.
And I can answer that, and the answer is 15,000 births.
Correct.
Roughly.
But that's the initial assumption is a big assumption, right? You're assuming if the world was, following that certain distribution, then this is the number of samples you needed. But we don't know that the initial assumption, what the initial distribution is.
No, we don't. I think this is a useful number in the sense that this is a useful interpretation. I could ask, if P was true, how many observations from P would I need before I could favor P over Q? That gives me I can interpret that number. Now it's not just a number, right? It's not just 7, it's 7 decibands, and that can mean something to me. Like the number being small, I can compare it to something I feel like I can experience.
Alex, I have a question. For this particular setup, we've chosen 2 hypotheses, like 5149 and 50-50. But it's easy to imagine a continuum of all Bernoulli distributions with P between 0 and 1.
Yes.
How does this framework change, or does it accommodate the idea of a continuum, or not even a continuum, but an n greater than 2 hypotheses?
So that was kind of asked a little bit earlier, and the weight of evidence in the way that we're describing it, not particularly, but you can start to consider things like if you had a space of all possible things, like all possible theta, you could compute the weight of evidence in favor of one of those thetas versus all the rest, if you were willing to marginalize out the theta. And then you're really doing sort of Bayesian inference the way that you're kind of used to, or the way that most people do it. I thought there was some utility in talking about the binary case, both because that's common and also because that is most relevant for things like KL, where there's 2 hypotheses in question. I wanted to show this movie, and I don't know if my computer is going to, but if you go, I don't know if my computer's having problems. I'm trying to talk to too many people and blah, blah, blah. But it's a really cool movie. It's on Twitter. You should watch the slides. You should watch the movie. It just shows 2 continuous distributions morphing and what the KLs are. I didn't produce it. Somebody tweeted it, but it gives you you could look at KL changing. But in interest of time, I'm going to skip it now, but definitely check it out. Okay, the next thing, I'm really running out of time, but kind of a couple things I kind of want to more or less scattershot at you. And we will talk about, I want to do some service to this stuff, so we'll talk about it next time. But I want to leave you with the idea that we could use this, once we interpret KL divergence, relative entropy, as a change in our updates of belief, we could use that as a principle for learning. And we could say, why don't I set the parameters of my model? or maybe this addresses Daniel's question. I want to set the values of my hypotheses, the values of the parameters of the model, such that they are as close as possible. They require the smallest update with respect to reality. And so I could try to minimize the KL divergence between reality, whatever the true distribution in the world is, and whatever my model is. And it turns out that is what we do when we use cross entropy as a loss function, when we do maximum likelihood learning. It is equivalent to attempting to minimize the distance between our model and reality. We're trying to make it so that in light of the evidence that we see, the data, we want to minimize the weight of evidence against our model. We want to make sure that our model is as close to being favored as possible. That's what kind of cross entropy and maximum likelihood learning is. In practice, there's a caveat. We don't actually have the true distribution. So we split the terms into pieces and we use the empirical distribution. We assume that the distribution of reality isn't some smooth thing. It's a bunch of delta functions on the observations that we achieve. And then we compute the empirical cross entropy. But this also makes light why this is a problem. Because then what we're actually doing is we're asking our model to get as close as possible, not to reality anymore, but we're asking our model to get as close as possible to this monstrosity as possible. We're asking our model to match a bunch of spikes on the data points that we observe. And then we often cry foul when it does precisely that. Okay. The next two things we wanted to talk about, and we've run out of time, but I want to talk about entropy and mutual information. I just want to tell you what they are, and then we'll talk about them next time. But I want you to think about entropy as being a relative entropy, but relative to the uniform distribution. The relative entropy was a measure that we could use between two distributions. If I wanted a number I could assign on a single distribution, then we have to choose some kind of convention for what the second one is. So let's choose as a convention that we take as our second target uniform, because that seems like a useful target. If you compute the relative entropy between any distribution and uniform, that is up to a minus sign and a constant, the entropy of the distribution. And you can use that to all of your existing, you can bring in all of your existing intuitions for what entropy is and stuff like that. And then mutual information is also a KL divergence, an expected weight of evidence. But in this case, it is between, we're interested in a question about two random variables. And so what we do is we consider two hypotheses. One, that the two random variables are jointly related. They come from some single joint distribution P of X and Y. And the alternative hypothesis is that they're independent. And they come from the corresponding product of marginals. And how much evidence can I accumulate that these two things actually come from a joint distribution rather than a product of independent distributions? Okay, and at that point, I'm out of time. I want to apologize. I wanted to talk much more deeply about what entropy and mutual information is. I will talk about it in the chat, but if people do want to hear sort of more of an intuitive take on those things, we can start next time by doing that. I think that's totally fine. Or we can focus on applications. Please tell me what kind of applications you want to hear. Please check out the problem set. Interesting problems, some of which will get you kind of thinking about these things in deeper ways and interesting ways. Please talk about it on the chat. Please tell me, give me feedback, give me stuff. Thank you for your time. A lot of people are late. I'm happy to hang out here and sort of talk more, but I want to officially, bless you all to leave if you need to go. Okay.
This was really, really cool. Thanks so much, Alex. That was looking forward to the problem set and the next lecture.
Yeah.
Same here. Really good. Yeah.
Thank you.
So I will stop the recording now, just so if people want to continue to talk to you, they don't have to do it on recording.
Yeah.